Alright, and problem number 7, it gives us some information. We have to solve the problem. Now, a lot of people just forgot this problem altogether. Part A. The figure shows the disk as a coin can be viewed from above. Draw and label the vectors on the figures to show instantaneous acceleration and linear velocity vectors. Even though it's a force, even though you think forces with vectors, anything can be a vector. Anything that has direction. So it says draw and label the vectors on the figure to show instantaneous acceleration. The third time. There we go. So on this object right here, where is the acceleration? Don't ever have to worry about this. Acceleration is always, always, always to the center. Right? So I can make this to the center. So that is your AC. Next, we talked about velocities. Well, we knew velocities are tangential. So right here, that is tangential to the radius. Now, next, determine the linear speed of the coin. Now, what a lot of people may want to do is do F net, which the force holding it is friction, equals mv squared over r. Problem is, I don't know the force. Whoops. I don't know this one. Sorry about that. I don't know the force, and I don't know the velocity. I have two unknowns, can't solve it that way. So maybe go back and look up here and see what we're given. I need to see if I have a distance and a time. Right here, it says it takes 1.5 seconds to do one revolution. That is a distance and a time. So I go 1 revolution in 1.5 seconds. Now we can do some dimensional analysis, multiply by our conversion factor. We want to get rid of revolutions and go to meters. 1 revolution is 2 pi times r, which is 0.14 meters. Okay, that's a 0.14. So then I'm left with a velocity that you can write down for that one. Okay. Now the next one says, that was part B. The next one for part C says it's the rotation rate. So how fast it rotates, or the velocity is gradually increased. Determine the linear speed of the coin when it begins to slip. So when it begins to slip, that's right when you're starting to overcome the force of friction. So you're using it all. So on this one, I can go back and look at this equation here. The force of friction is mv squared over r. Now we said here you don't know the force of friction, but that is mu Fn equals mv squared over r. Okay. If you were looking at the coin on the turntable, it has gravity going down and normal force going up. It's not accelerating up or down, so they're equal. This goes even a step farther here, and then they will get to mu mg equals mv squared over r. Math is in both terms, so they cancel out. So I was trying to find the velocity. Well, here the velocity will equal, looks like mu g times r, and it is the square root of mu g times r. Plug in your numbers and you'll get a value. The last part, D, says if the experiment were repeated with a second coin on top of the other one, how would this affect your answer? Well, the only thing you do when you put another coin on is increase the mass. So I get more mass. Right? Let's see if mass affects that. If I look down here in this equation, is mass there? It's not there. So if mass isn't there, it cancels out for the velocity, then it doesn't affect it. So everything would be the exact same.